Hello everyone and welcome to our final year project video. We are Cloud Genesis and our project is achieving energy efficiency on the edge through containerization, a brownout approach. Background of the project. As you may know, the edge has multitude of applications. It allows the data processing closer to the data source, reducing latency and enabling operation even in low or no internet connectivity areas. However, these edge computing environments face significant challenges such as weak computing power, limited memory capacity, limited storage capacity, and limited energy capacity as they would be mainly powered by batteries or inconsistent renewable energy sources in remote locations. Also, containerized applications are gaining more popularity in the current context, and we identified a lack of research investigating the problem of low energy availability for containerized applications in edge computing environments. Therefore, we are addressing this problem by utilizing a container orchestration-based approach for achieving energy efficiency in resource-constrained edge environments while maintaining quality of service. The approach we are suggesting to address this problem is a brownout approach. The brownout approach we adopted is a container orchestration-based technique that selectively activates and deactivates microservices to reduce energy consumption without impacting the main functionality of applications. In a microservice architecture, applications will consist of both mandatory and optional services. Using the brownout approach, we can deactivate optional services that do not need to run continuously, saving energy. Methodology. Our proposed system architecture comprises two main components, the power model and the brownout controller. The power model predicts the edge cluster's power consumption based on the number of worker nodes, containers, and the total CPU utilization of all deployed containers. This prediction is then fed into the brownout algorithm, which is the core component of the brownout controller. The brownout controller comprises the brownout algorithm, policies, actuators, and the activator. The brownout activator gets the battery percentage from the battery monitor, and if the battery monitor is lower than a certain threshold, it will start the brownout algorithm. So, when the algorithm runs, it will utilize a policy to select how to deactivate optional containers or nodes to reduce power consumption while maintaining the required QoS. You will gain more insights about this in the latter part of the video. As mentioned above, the power model is used to predict the power consumption of the edge cluster, taking edge computing cluster characterizations such as total CPU utilization of all active containers, number of active containers, and the number of active worker nodes as inputs. Here you can see the equation derived to compute the power consumption. It shows clearly how containers and worker nodes contribute to power consumption. The constant C1 represents any power static values dedicated to background processes that are constant throughout the period. The experiment showed that the coefficient C2 has the highest value, depicting that number of worker nodes has a high impact on power consumption. This indicates that in edge clusters running containerized applications, taking steps to reduce the number of worker nodes will have a greater impact on achieving energy efficiency. The brownout algorithm is the main component of the brownout controller, which fulfills the objective of reducing the power consumption of the edge cluster while maintaining the QoS. The QoS parameter we intend to maintain throughout is the success ratio. The definition of success ratio can be seen in the equation shown. So we will deactivate containers or nodes so that the success rate is within an acceptable range. If we move our attention towards the brownout algorithm, according to the flowchart, the brownout algorithm checks if it is activated. The activation is determined by the brownout activator component, which activates the brownout algorithm based on the battery percentage. If the battery percentage is below a threshold, it will activate the brownout algorithm to start saving energy. If not, it will stop running the brownout algorithm. When the algorithm runs, if the battery percentage is below the low threshold, the brownout algorithm gets the current success rate from the cluster. It compares it to the acceptable success rate predefined according to the application demands. If the CSR exceeds the ASR, we can deactivate optional containers. The algorithm calculates an upper threshold for power consumption while considering QoS using the equation you can see in the flowchart. Basically, a threshold power is calculated such that the application success rate will be within the acceptable success rate and minimum acceptable success rate. In the equation calculating the upper threshold, the CP value is a constant value that depends on the container deactivation policy. Lower values of the constant CP are optimal. The algorithm then calls the deactivate containers method to bring the power consumption of the edge cluster to the calculated threshold value, giving it as an input parameter. In this step, one policy will be used to deactivate containers. After deactivating the containers, the algorithm enters a sleep state for 5 minutes to allow for settling before repeating the process. Furthermore, in this algorithm, we check the condition if CSR is lower than MASR because we want to keep our success rate above the MASR. If it is true, containers will be activated back to ensure the success rate will be above MASR. Furthermore, if the cluster is above the higher battery threshold defined, it will activate the containers back to run the applications at the cluster's full capability. In the NISP policy, the main objective is idling nodes to reduce power consumption. So, it will select nodes in ascending order of utilization and idle till power consumption goes below the computed upper threshold. In a case where the power consumption will be reduced higher than expected, without deactivating the final node selected to deactivate, we will apply the LUCF policy to the containers in it to deactivate some of the containers and reduce the power consumption as necessary. Implementation and evaluation. For the validation and verification of our model and policies, we use the shown experimental setup. Regarding the power model experiments, the data were fed into an exploratory data analysis model to plot and observe the relationship to power. The values obtained for the coefficients show that the number of worker nodes and container CPU utilization sum has the highest impact on power. At the evaluation, the power model demonstrated an accuracy of over 80% with an R-square value of 86.3%, indicating a good fit of the predicted values to the actual values. The evaluation of the Brownout control is carried out on a representative application deployed on Kubernetes. In our experiments with the Brownout controller, the NISP policy showed a power saving of 34.07% and the lowest CP value of 0.8199, making it the most optimal policy among the ones we tested. The developed Brownout controller is delivered to the client using an open source client application we developed. This application can be deployed within the Kubernetes cluster or externally and connected to the cluster. The application will include the Brownout controller API and use a dashboard which exposes the Brownout controller to the client. We developed an open source software application that contains the Brownout controller, the API developed using Go and Gorilla Mux, and the user dashboard developed using React and Chart.js. This is a small demonstration of the usage of the dashboard. At first, the Brownout controller is at the deactivated stage, so we can activate it with this switch. Then the current battery percentage of the cluster is shown, and since it is lower than the low threshold value, it will run the Brownout algorithm. Then also we can see these instantaneous values retrieved from the cluster. This chart shows the variations in utilization and in success rates. Furthermore, in the configuration page, we can set the variables according to the user's requirements, so you have the opportunity to change these variables. In cluster page, you will see the deployments and the number of replicas of each, and then the nodes and its statuses. Coming back to the dashboard page, if we let it stable for a few minutes, we will see the power consumption drop with the activation of the Brownout controller. After about 1 minute after switching on the Brownout controller, we can see how the current power consumption is at 16.83 watts and how the active part count has dropped from 60 to 35 and how the active node count has dropped from 8 to 6. And also we can see in this chart how the power consumption is lower than before.